Then, of course, if you go back to paper-based diagnostics, we have talked of chromatography, and in chromatography, I told you that this is basically you can have a mixture of several substances here. So this is ink A, B, C, D, let's say colored substances. As they move to the stationary phase, based on their differential mobility on the stationary phase, they'll separate out into different bands. And most of you would have done paper chromatography in your 12th experiments or in BSc, so you would know. And the most important why paper chromatography is important to us, because paper-based diagnostic tests are very easy to use, right? And they're very inexpensive also. Paper can be molded, can be printed, can be any chemical can be added to it. Paper itself is highly inert, so no reaction is expected from the paper or cellulose itself. So therefore, paper-based strip tests become very important to us. And the most important and the most commonly used paper-based strip test that we've used is your pregnancy test kit, and we'll discuss that in a moment now. So what is this paper strip test based on? So it is based on the principle of lateral flow assay, right? So a lateral flow assay is a strip test which is based on the capillary action of the paper. There are 4 areas on the lateral flow assay. First one is called the sample area, where of course you're going to load your sample. Then the sample flows down to what is known as a conjugate pad. In the conjugate pad, you have antibodies which are not fixed, so they're not immobilized. So your antigen will bind to the antibody and continue to move. Then you have the test line. In the test line, you have antibody against antigen. So here you'll have your sandwich and your antigen will get stuck here, right? So this is your test line, which will give you a color. Here you have another antibody that can bind to the primary antibody that you've used. And that gives you the control line. So control line is basically a reaction between the primary antibody and the secondary antibody. So even when there is no association of the analyte with the primary antibody, the primary antibody will move through it and it will come to the control line. It will still give you a color test in the control line. So in a positive test, you will have color development in the test line, also in the control line. In a negative test, you will have only the development of color in the control line, not in the test line. If you do not have any color development, you know something has gone wrong. If you have a color development only in the test line, not in the control line, then again, your test is futile. It is not meaning anything because the test has gone wrong. So positive test, you will have 2 colored lines, both in test line and the control line. Negative test, you'll have color development only the control line, not in the test line. Any other thing is a false result, right? And not to be believed. Beyond this is an absorbent pad where the excess liquid will be absorbed. And this is basically encased into a plastic strip so that the paper is kept unmoistured and undamaged till the time you go for a test. And you are given a manual along with it so that you can compare what is a positive and what is a negative. So this is the idea of a point of care test. A simple paper strip test without too much of complications. Anybody can do it, anybody can understand it, anybody can estimate what is happening, right? So that's the idea of a simple test. There is an FDA definition of a simple test. This is a simple test. And why nanobiotechnology becomes important here? Because use of antibodies conjugated to gold increase the sensitivity of the test. So the sensitivity of the test increases. And as I've shown you in the earlier reaction also, that allows for nanoparticles to be used in this kind of ELISA assay. So this is basically an assay for development of color here, right? And here you're using fluorescent markers. So this is not exactly ELISA, but yes, kind of ELISA in the sense there is an antigen-antibody reaction, which is being reported in terms of color because of the accumulation of gold nanoparticles, right? And depending on the size, you'll have different color. You remember gold nanoparticles. So here you'll use a specific size so that you know what color line you're going to develop when there is a positive test. So design principle for paper-based diagnostics is you have a lateral flow. This is your lateral flow assay. And then, of course, in the lateral flow assay, there are 4 chambers: sample pad, conjugate pad, test line, and absorbent pad. And then, of course, you know what happens in the reaction. Whether any binding happens here or not, binding would always happen here. So this test will at least give you 1 color line, right? That is also important. And that could be a question. What is the minimum number of color lines you'll get in a lateral flow assay, right? And that only tests how much you have understood. Remember, all exams will test how much you have understood, right? When you go for a NET examination, it is not about how much you've crammed. When you go for a PhD interview, it will not be about how much you've crammed. It will be about how much you have understood. A person like me with no biotechnology background could crack the CCMB interview only because when they asked me question that I read, I had some clear idea of things, right? So coming back here, this is your strip test based on lateral flow assay design. The sample to be tested flows from one end of the strip to the other end by capillary action. So this is a paper, and by capillary action, the sample keeps flowing in the direction from left to right. And these are our areas. So this is the sample area, this is your conjugate area, this is your test line, this is your control line, and then of course the absorption path. As the sample flows from the sample spot, it interacts with mobile primary antibody against the analyte to be tested. This is the conjugate pad. The antibody is mobile, so it keeps moving. Followed by interaction with the immobilized secondary antibody in the test line. So here in the test line, you have immobilized secondary antibody. So once it gets fixed here, then it doesn't move any further. The unbound primary antibody interacts with the secondary antibody in the control line, which also yields a color reaction. So this is your second color reaction. The development of two color lines, both in the test line and the control line, indicates a positive test, right? The development of color only in the control indicates a negative test. So positive and negative must be very clear. The most common paper strip test, or the most common lateral flow assay test that we've used, this is called human pregnancy test, right? And the analyte you're testing for is the hormone called human chorionic gonadotropin. It is a protein hormone. You can have antibodies against it. So this is known as human chorionic gonadotropin. The sample here is urine. So you could have questions of what is the sample for the pregnancy test, what is the analyte you're testing for, and then what could be the positive result. Positive will be development on both lines, and negative will be development only in the control line, not in the test line, right? That's the whole idea here, right? Human chorionic gonadotropin, the concentration of chorionic gonadotropin increases midway through the pregnancy and then goes down. So therefore, this is a good indicator of pregnancy. Right? This is glucose biosensor. Glucose biosensor is important to you because it was the first biosensor to be developed way back in around 1970s by Leland Clark, who is the father of biosensors. Photo भी बनी हुई है एक slide में अगर देखा हो आपने, ठीक है? Here you are. This is your sample pad in hand. So here you load your sample. Then this is the control line, and then here is the detection zone. In the detection zone, you have your glucose oxidase enzyme, right? Glucose oxidase. This is the common enzyme that is present in all glucose tests, whether it is first, second, or third generation. We have not gone to second and third generation as of now. But here in this case, this is glucose oxidase. And glucose oxidase converts glucose to gluconic acid, and the electron acceptor FAD is reduced to FADH2. You could have a question, what is the electron acceptor in case of glucose sensitive? So that is FAD, right? And then FAD is reoxidized, and in the process, trimethylbenzidine gets converted to oxidized trimethylbenzidine, which develops a color reaction. So paper-based colorimetric biosensors for tier glucose measurement enzyme used as glucose oxidase. So one important difference here is that this is meant for this. Here you're not testing for blood. You're testing the glucose levels in tier, and then you're correlating it to the glucose levels in blood. And the major problem with such tests is, and if you've done your quiz, you would see there was a question: what is the major limitation of these wearable biosensors or other type of biosensors? So one of the major problems is that these body secretions that you have, like tear, sweat, or for that matter, mucus, they may not have exactly the same composition of metabolites as present in blood. So there is not a direct correlation between what you measure with the level of glucose you measure in tear versus the level of glucose in blood. So that is one of the major limitations of these tests, right? But of course, we are moving to wearable biosensors, which are non-invasive. They do not prick your skin and they do not reach your blood, right? So that is, again, something that to keep in mind. And then, of course, there is a reference here. You can match the intensity of the color with the color developed here, and that will give you the concentration of glucose you have in your tear. So this could be largely a test that could replace your everyday injection to test for what is the glucose level, right? So this is glucose strip test. The reporter molecule is trimethylbenzidine, and tetramethylbenzidine